Okay? And then he looked at the other thing that's bright. He looked at the brightest thing out there, which was Jupiter, and then he drew this. And I want to draw your attention now to the fact that Jupiter itself is encircled by 4 other stars. It's very weird that Galileo's drawings are so pixelated, but it's the kind of technology. Yeah, he didn't have Microsoft PowerPoint. So what are these? These are the Galilean moons. Okay, the moons that encircle the planet Jupiter. What's interesting about them? Well, first and foremost, these objects orbit Jupiter in a matter of days, just like extrasolar planets. Secondly, if you were to take them, okay, and take Jupiter itself, as well as its satellites, and blow them up such that Jupiter becomes a mass of the sun, and you were to ask what kind of planets would these become, they would be the typical extrasolar planet, a few times more massive than the Earth, and yet a few times less massive than Uranus and Neptune. So even though the solar system itself seems a little bit weird, the satellite system of Jupiter, right, looks like a miniaturized outcome of the standard outcome of planet formation throughout the galaxy. Okay? So inspired by this, we decided to look into this problem more closely. Now, both planets and satellites do not just appear in isolation, right? They appear during the first few million years of the lifetime of a star, when stars are encircled by these thick disks of hydrogen and helium gas, as well as dust. And this is not a picture from 4.5 billion years ago. This is an artist rendition from one of our models, but the young Jupiter would have looked something like this, where it was encircled by this cloud of hydrogen and helium gas, which also had a substantial dust component. And what we found out early in our work, that dates back now a few years, is that even though we were, of course, none of us were there 4.5 billion years ago, one of the things that we can do is to use our understanding of the laws of physics to recreate what the formation of satellites of Jupiter must have looked like. Okay? And what we found is that the Jovian disk of hydrogen and helium, right, stuff that surrounded the young Jupiter, was an excellent trap of dust. So dust grains, right, much like the ones that are floating around this room somewhere, would get trapped in this disk of hydrogen and helium gas around Jupiter, and subsequently, once their mass became large enough, they would collapse into to basically icy asteroids. Okay? And subsequently, upon this system of icy asteroids that orbit Jupiter in a kind of a ring would unfold, right? Their gravity would cause them to stick together and grow into the satellites. That said, once the satellites reach a critical mass, the disk starts to pull them in. And if you're carefully watching the outcome of this computer model that we've done, those orbits are slowly shrinking, right? And that is a key element, okay, that we've discovered, is that if you let this whole system unfold, right, let it evolve under its gravitational and hydrodynamical evolution, there exists a critical mass scale, right, that once reached allows the orbits to leave their feeding zone and stop growing. That's why Io, Europa, Ganymede, and Callisto, the satellites of Jupiter, live close to their host stars. Okay? And that's why they're all kind of the same mass and the same size. They grow up until the disk pulls them in. Okay? So we were pretty excited about the kind of outcome of all this, the ability to, in a nearly perfect manner, reproduce the architecture and the masses of the Galilean satellites. And we immediately thought, upon figuring this out, that okay, what happens if we now apply this understanding to planetary systems more broadly? Okay? And here it helps to take a look at the photos that we have of young stars, okay, and the disks that surround them. So these are all stars younger than 4 million years. Okay? And you can see that they're encircled by disks of stuff. And in particular, all of the solid material, the dust, goes into these rings, just like in our computer simulation a few slides ago. So what happens? Well, this is a picture from a paper that we just published literally a couple of weeks ago. But rather than explaining this specific picture, I'll show you a video of what we obtained. Oh, see, I'm just not good at clicking. Okay? Like, I keep going back and forth. Okay, we're gonna try this one last time. Okay, now it's gonna work. Okay, so this is an outcome of one of our computer models where the dust self-consistently collects into this ring, and within this ring, a planet emerges, but upon growing to a sufficiently large mass, gets pulled in by the disk. And this leads the way to the second one forming, and so on and so forth, which leads to the emergence of large-scale uniformity among the planetary systems that was discovered by my colleague, Andrew Howard. Okay? So all of this is here to tell you that somehow the process that makes the moons of Jupiter and the process that makes typical planets that orbit other stars is the same process. But I believe I'm yet to answer the question of why is the Earth different? After all, the Earth's orbit, if you haven't noticed, lasts a full year. It doesn't last 3 days, right? So why is it that the Earth escaped this particular evolution sequence? And the answer is simply that within this sun's protoplanetary disk, right, the disk of hydrogen and helium that encircled the sun during its first 4 million years of lifetime, the ring of solid material from which the Earth emerged was low mass. Okay? It was so low mass that it took the Earth longer to form than the 4 million year lifetime of the hydrogen and helium disk. Instead, the Earth took hundreds of millions of years to form. Why? We think we understand the answer to this. And we think that the answer, the culprit, as to what makes the solar system special is actually Jupiter. Because Jupiter, upon forming, right, cleared out this giant gap in the solar system's disk and prevented the flow of solids from replenishing the Earth's local environment. So with this thought, I want you to think about the following, right? What this suggests is the fact that the presence of giant planets like Jupiter is kind of a prerequisite to the emergence of low-mass planets like the Earth. If Jupiter was not there, then our Earth would evolve to be a big multi-Earth mass body that would capture a huge hydrogen-helium atmosphere, and then we wouldn't be able to do astronomy, okay, because we wouldn't see the sky. Okay? Moreover, that none of the sunlight would penetrate down to the Earth, photosynthesis wouldn't work. Right? So perhaps the fact that we are having this conversation is something that we owe to the emergence of Jupiter, at least if this theory is correct, which I totally promise it's totally right. So with this thought, I actually want to hand this over to my friend and colleague Mike, who's going to dive even deeper and discuss further.